Hi friends, my name is host Eric. I'm host Talking with Famous People. I'm also a logic teacher, and I was in fact just today working on these truth tables, 3 variables truth tables, with my very bright 6th grade ISTP girl who picks it up like PAM. It's incredible, it's beautiful. Anyway, I made some statements about the negation of conditional in a previous video. I'd like to explain what I meant, and I may have misspoken in it as well, I'm not sure. So here's the deal. What I was referring to is a rule of equivalence or a rule of replacement, it's called, in conditional logic. So traditional conditional logic can be broken down into rules of replacement and rules of inference. Rules of inference are ones that allow you to say if P then Q and P therefore Q. Rules of replacement replace things with equivalence. Now, each of these equal signs here should have 3 lines on it, not 2, to mean logically equivalent to. But I don't have a 3-line equal sign on my keyboard. So, anyway, first thing to note here about a conditional if P then Q is that according to a rule of replacement called material implication, you can convert it into not P or Q. I may have said in the video not Q or P, in which case that's why you were confused, Raen. It is, in fact, not P or Q, because, obviously, if P then Q means you either have P, in which case you have Q, or you don't have P, in which case you may or may not have Q. So, material implication is a rule of replacement that you use to convert that thing. Now let's look at the negation of a conditional. The negation of a conditional is represented here as not if P then Q. I can still use material implication, the rule of replacement, inside the parentheses before I apply the conditional. And I end up with this, not P or Q. Now, DeMorgans Theorem, it allows you to convert either of these ways. If you have not and, you can convert it to not or not. If you have not or, you can convert it to not and not. In this case, you've got a not or, right? You got the negation. It is not the case that an or. So what you do is you apply DeMorgans Theorem and you get not P, which is P, and not Q. So what's weird about this is if I say something like, it is not the case that if aliens exist, then it is not the case that if it rains gold coins, then aliens exist. Then it must be the case, according to this, that it both rains gold coins and aliens don't exist. Now, that's a weird sort of flaw of conditional logic, I guess. If it's not the case that if it rains gold coins, then aliens exist, then it is both the case that it rains gold coins and that aliens do not exist. It's the negation of the truth table of a conditional. So it's a little quirk in conditional logic that I've noted before as representing the barrier at which natural language is actually represented by conditional logic meaningfully. And I hope that answers Raen's question. Anybody else who was curious about the negation of a conditional, it allows you to make some crazy, weird, valid but unsound arguments if you like to play that kind of game.